So, hello guys. This is my first paper club, and it's a pleasure to be here presenting to you in what I may say is the best Friday of Brazilian year. So, lucky day. I'll be presenting the paper that is entitled Rho-1, Not All Tokens Are What You Need. This was the runner-up best paper of NeurIPS in the last year, 2024. They published in NeurIPS with the title Not All Tokens Are What You Need for Pre-Training, but they are the same paper, just this is the version that is on arXiv. Before just diving into the paper, I'm just gonna do a brief review of how large language models are usually trained. In general, they're trained. The standard approach is to use something called causal language modeling, which is just a fancy way of saying that it predicts the next token. Usually, I think this is very clear, but you get a sequence of tokens, and the goal of the model is to predict the next token. So in this example, for instance, you'll get like a batch of sentences, a batch of sequence of tokens, and you'll just pass each sample, and you just split it into tokens. And for each token, you try to predict the probability of the next token. So the loss function is all based on predicting the probability of xi given all the previous x's. And there's something important to it that is important to this paper. That's why I'm talking about this, is that each token in the sequence has a token level loss that they refer a lot in the paper. So for each token, you just get the probability of the next one. And for example, if you want to know the loss of the token magic, you will just get the probability of the token magic given all the previous tokens. And you're just gonna compare it to that one hot encoded way of representing the token magic, right? It's just a usual classification loss cross entropy. So the loss of each token is given by the loss of x1, for example, is minus log of probability of x1 given x0. So you do that for each token, you have the loss of each token. How well does your model predict that token given all the previous ones? This is a token level loss. But in the end, what we do and what we really consider when we're training these models is that we just average them all, average all the token level losses, and you get the total loss of your model. This CLM stands for causal language model. So I'll be referring to it as CLM. And as you can see in the final loss, it's just like the average of every token loss probability. And it's an arithmetic average. It's not, it considers all the tokens to be the same. All the tokens are equal in the loss. And the paper starts with this example of why this may not be the most effective way of training these models. So it starts with this sentence. The farm has 35 hens, a random date, and 12 pigs. Then a random ID says totaling 47 animals. So as you can see, you have these undesired tokens. They're just noise. They're not contributing to the training in any way. But anyway, in the normal way of training these models, this causal language modeling, all of them are considered in the loss. That's what you have here to the left. What they propose is to use a selective language modeling instead, where you would really select the tokens in which you're going to compute the loss. Instead of just averaging them all, you would just choose some tokens and train only on them. So back here in the example, for example, if I decide, and I'll just get to that in a moment of how we decide, but if I decide that begins and tonight, for example, they are noise. They are not good tokens to use to train. So I'll just select Carnival and Magic. Then instead of averaging over all these 4 tokens, I would just average between Carnival and Magic, right? I'll just consider their token level loss and discard the other losses. So this is the premise of selective language modeling. So, okay, now let's really start going through the paper. I did not prepare like a slide presentation. I think this is a very well-structured paper. I recommend reading. It's very complete and very reproducible. So I'll just go through it. Then I can share like the ones with this highlights in our channel. So yeah, they argue that usually nowadays the most popular approach is just scaling up things, scaling up models, scaling up data sets. However, sometimes you just scale your data set and get like the whole internet, but you also get a lot of noise. I think this is very common sense, right? Our data is very noisy out there. So they say that data filtering has become something like crucial for training these models. And usually the methods that do this data filtering, they do this in a document level filtering. So they filter basically the sources of the data, but not the tokens. It's not a token level filtering. It's a document level filtering. So yeah, they say that still if you curate high quality data sets, you still may get some noisy tokens lost in the middle of the text. And that because of that, maybe using the same exact loss for all the tokens is not very effective, right? You're gonna just waste some computation power computing the loss of tokens that will be useless for you, or they will just harm the performance. So this is not effective. One thing that the guy that presented this paper in NeurIPS said is that you need to make things like, instead of just thinking about scaling stuff, we are reaching a point where we almost exhausted all the data available. So from now on, he pointed that maybe some good paths to study is how to get the most out of the data that we have instead of just scaling things up. This is something that he says in the presentation. So yeah, the first thing that they do to start their study is to make a study on how the token level losses change during pre-training. They want to evaluate for each token in a data set how their loss evolves during pre-training. So what they do is that they get a small model, the Tiny Llama 1B, and they train it. They keep pre-training it with 15 billion tokens from Open Web Math, which is a data set. And what they do is the following. Let me go back here. They do the following. They get this 15 billion tokens of their training data set, and they get the first 1 billion, and then they train their model, keep retraining the Tiny Llama on that 1 billion. After that 1 billion, they pause the training. Then what they do, this is a checkpoint. They pause the training in every 1 billion tokens. So they pause their model. Then they have a validation set of 320,000 tokens. This is another set, a validation set. They get all these 320K tokens and pass them through the model. So in this case, instead of having like 4 tokens, you would have 320K tokens. You pass through the model and you get each one of these losses. So we will have 320K losses, individual token losses in the end. So, okay, they store these losses. Then they keep training for more 1 billion tokens in the training set. Then they pause again. Then they assess again the loss for the validation set, the 320K validation tokens. And they do that for every 1 billion tokens of the training. They do this checking on the validation set and they store these results. Then in the end, what they have is basically the history of each token's loss along the training, right? Okay, then they have this data. What they do is that they categorize this data in 4 categories. The tokens that started with a high loss and ended with a high loss, the ones that started with a low loss and ended with a loss, the ones that started with a high loss and ended with a low loss, the ones that started from low and went to high. So yeah, the 4 combinations of losses. And what we expect, what I was expecting, what they expected, was that most of the tokens would fall into the category of starting with a high loss and decreasing the loss, right? That's the whole point of doing the training. But that's not what they found. They found that only 26% of the tokens showed that behavior of decreasing the loss along the training. Most of the tokens, they remained in the low loss. They started already with a low loss, and the loss did not change much over the training. Then they also say that they have 11% of the tokens that are persistently challenging, that started with a high loss and ended with a high loss. And they discussed that this might be due to like noise, really some noisy tokens. And 12% of the tokens, they have a loss increase. And they don't discuss a lot about why is that. Why would a token start with a low loss and end with a high loss? But this accounts for 12%. So here, let me just zoom in, too much. I think you can see, right? This is how they plotted it. So each of the lines corresponds to one of the categories. As you can see, this blue line here is from the tokens that started with a high loss and ended with a significantly lower loss. But many of them just stayed in the same level that they started. And another observation that they made is that for these tokens that remained low or remained high, they plotted some individual tokens of these categories, and they said they saw that they have a high variance. So it's very high variance in the way that they behave, their loss behaves during training. So it just goes up and down. In the end, it's basically the same level of loss, but it varies a lot. Okay, so that's what they say here, high variance, noisy tokens. So what they conclude from that is that even though the loss of the model as a whole is decreasing over the pre-training, each token behaves differently. Some of them have very different behaviors from each other. So that kind of builds on top of their work of, okay, maybe if the tokens behave differently, we should treat them differently during the training, right? So, okay, that's why they develop what they call a selective language modeling. They train a model that they call Rho-1 with this approach of selective language modeling, which means instead of selecting all the tokens, instead of training all the tokens equally, you will select what tokens you will train on. Just a sec. Okay, so they do a token level data selection. That's what they do. How they do that? So they start by training what they call a reference model that is trained specifically on a high quality data set. So they just curate a high quality data set, high quality data, very little noise, and they train their reference model. Then they do the following. Let's go back to ScholarDraw. So they have their reference model. I'm calling it RM. And then they have their pre-training corpus, which is actually the data set you want to train your model on. They call it pre-training corpus. Then you pass this whole pre-training corpus with all your tokens that you want to train. You pass these tokens through the reference model. So imagine that these 4 tokens are your whole data set. And you pass them through the reference model, and you get the token level loss of each of the tokens. This is what I'm calling all LRM. They call L delta, but I couldn't write delta here, but it's the same thing. The LRM is the same L delta that I'm going to show in the paper. Then what they do is that they get all these losses. And then here, the SLM is the actual model they're training. So yeah, they get their data set. They pass their data set through the model they're training. Just to be clear, this reference model, it is trained in the beginning of the pipeline, then it is fixed. You don't train on it anymore. It's just a reference model. This is the actual model you're training. Then, okay, you're going to pass your data through your model, and you're going to get their losses, right? Then what you do is that you compare your losses to their losses in the reference model. So for example, you have, I don't know, you have like this LX1, which is the token level loss of magic. And you just compute it in your model. Then you also compute it in the reference model, and you calculate this excess loss, which is basically the difference between your loss in your model and the loss in the reference model. So just a moment. This is the formula. Like just LXS is the loss of your model minus the loss of the reference model. Simple as that. So this is the excess loss. What's the intuition behind it? Is that the higher the difference from the loss in your model compared to the reference model, the more you need to learn that token, right? Because if your model, for a given token, your model has a high loss in that token, it means that it did not learn that token well. But if for the same token, it has a low loss in the reference model, which is the good model, okay, it means that you're, I don't know how to say this word in English, but you have like a discrepancy between the learning of that token. So you should focus more on learning on that token to get to the same level as the reference model. The goal is to match the reference model. Okay, then they calculate this excess loss. What they do then is that they just sort this excess loss for each token, and they get the top K%. So they get the K% tokens with the highest excess loss. I'm going to discuss this in a moment, but let me show here. I think it's easier. Okay, here they say that they get the top K% sorting by a score. In their main experiments, they're using the excess loss as the score. So this S that they're using to really rank the tokens is the excess loss I'm talking about. But later on, I'm going to show that they also experiment with some other scoring. So, okay, they just choose their tokens, the top K% tokens, and that's it. Then after selecting, they're only going to train on the selected model, so on the selected tokens. The other tokens will have their loss like multiplied by 0, basically, so it won't be considered. That's a very simple method of just selecting and selectively training your model. So, okay, let's see. So yeah, they select the tokens with the high excess loss because they're more learnable, they're more aligned with the desired distribution, because you assume that the desired distribution is what the reference model knows about. And you end up excluding tokens that have low quality or are irrelevant. This is something important. It's not just noisy tokens that are removed. Tokens that are already learned also don't need to be trained again. If the loss is already low, like if the loss is very low in your model and very low in the reference model, then you don't need to train again on that token. It's just wasting your computation. Okay. Yeah, here they say what I just said, that by default they use the excess loss as the score function, and it's only applied for the tokens that are beneficial for the language model. So let's go to the experiments. They use two scenarios. One of them is a mathematical thing, so they train their models on a math data set. In the other, they train on general data. So, okay, let's start by how they train their reference model. For the mathematical data reference model, they train on a 0.5 billion high-quality data set. So they curate this data set of high-quality math-related tokens. It's a very small data set, 0.5. Everything is small in this paper, as you're going to see. And for the general reference model, they use 1.9 billion tokens from some high-quality open source data sets. Also, their reference model is initialized with the same base model that is going to be used in Rho-1, in their model. It's going to be clear in a moment. The pre-training corpus, so the data set they use for the actual training. I've just said the data sets that they use in the reference model. Now the data set that is actually used for training their model. For the mathematical problem, they use OpenWeb Math. That is about 14 billion tokens. And for the general domain, they just combine 3 data sets, Slim Pajama, Star Coder data, and also the OpenWeb Math, which yields a total of 80 billion tokens. So, okay, a little bigger data sets. And okay, how they do the pre-training. Just to be clear, all these methods that they develop is for doing pre-training, not for fine-tuning on downstream tasks, okay? But I'm gonna dive into that in a moment. So, okay, for their pre-training, for testing their model, they get the Tiny Llama 1.1 billion parameters and Mistral 7B. 2 very small, fairly small models. So this is where they start from. And this is the starting point for both their model and the reference model, as I said earlier, that they use the same base model. Okay, so they continue pre-training on these two models. And okay, here they specify a lot of hyperparameters. As I said, it's a very thorough paper. You can reproduce it easily if you want, because it's very detailed. But one thing that I think it's important to highlight is the token selection ratio, that K% that I mentioned earlier. For the smaller model, 1.1 billion, they use a selection ratio of 60%. And for the Mistral 7B, which is a little bigger, they use 70% of the top K% tokens. Okay, and as baselines, how they compare their models. The most important comparison, in my opinion, is that they get their base models, Tiny Llama and Mistral. And instead of applying, they apply 2 settings. The first one is their methodology of the selective language modeling, and they keep retraining these models. And the other scenario is where they keep retraining using the normal approach of using causal language modeling and predicting all the next tokens without selecting any token. Like all the tokens are equal. That is where I started my presentation. So yeah, they call it, just to mention, this version that they keep training using the normal loss with all the tokens. They always add this CT suffix. So you're gonna see in the tables, that's what CT means, is that setting that I've just mentioned. Also, they compare their method with other baselines, top performing models, DeepSeek, Mistral, Quen. So they do a fairly thorough comparison. And okay, let's go to table 1. It's the first result that they get. This is in the math training set. So yeah, in general, in average, as you can see, just let me explain the table. This upper part here is the small model, 1.1 Tiny Llama, and it's compared to smaller models. And this other part here is when they trained with the Mistral 7B. And obviously they compare with a little bigger models, right? To be a fair comparison. They get, in the small model, they get in average, they test in various data sets, in average a 16.5 increase in performance. And as you can see, it gets a minus 40%, so a 40% reduction in the number of tokens used. So if you're gonna get like DeepSeek, it was trained on 150 billion tokens, and they train in only 9 billion tokens. So yeah, this helps a lot. As you can see, this tiny llama CT is the one that I mentioned. It is trained on all the tokens, so 15 billion. And this line here is the one with the selective language modeling. That's why it has less tokens. And something that I found particularly interesting is that, for example, when they compare to DeepSeek, this line. So comparing this line with this line, which is their model. Okay, they get a little lower performance in average. In some data sets, they get a little higher. So for example, in this one, it's a little better. In some other ones, also better. But in average, it's a little bit worse. However, DeepSeek math is trained on 500 billion tokens. And they get almost the same result training with 10.5 billion tokens. So it's so much more effective, efficient in how you really take advantage of the data that you have. I think this is the interesting part of the paper. Not exactly the results themselves, but how you can leverage your data in the best way possible. Let me see where I was. Okay, they also, another experiment that they do is not only for pre-training, but they also try to fine-tune it on downstream tasks, specifically on data sets with tool integration. So they use this Tora corpus that is a data set of problems that use external tools. And they also have fairly good results, not so good, but let me show here. So here they have their baselines, and here's where they compare. The one that has 1.1, the type that they fine-tuned, they continue the pre-training on the 1.1 billion, the tiny llama. It's not good. It's in average 56, 57%, which is way less than the baselines. But it is still better than just training with causal language modeling with all the tokens. But for the experiment with the Mistral 7B, they get fairly good results. So it's already comparable to the state-of-the-art baselines. They also highlight that it's particularly good at math and coding. So the data sets that involve math and coding, they shine a little bit more. So yeah, fairly good results even for fine-tuning on this kind of complicated task involving tool integration. Let me see what else. Okay, this is just like the general. Here they show the results. I've been showing the results on the math problem. They also evaluate in general data sets. They also see an increase. So in pink, you have their model. In white, you have, I don't know, gray maybe. You have the base model. And in blue, you have the one that was trained using all the tokens. And you see that mostly, I think everywhere, the pink bar is higher. So they have a better result across all the data sets. Okay, there's another point. Remember when I said earlier that they use a scoring function that in their case, they're using the excess loss as a scoring function, but it is not necessarily the excess loss. They can use other scores. So that's basically what they say here. Instead of using the whole, this is something that was questioned during their presentation in NeurIPS about the cost of training a reference model. And one thing that they do is that instead of using a reference model trained on high quality data, because you need to curate that high quality data. That's expensive. Instead, they just get their model, they get like their base model, and they train it normally, not using selective language modeling, using normal causal language modeling. Then they fully train it until they get to a good model. So they do that training on open web math. And then what they discuss is that more important than just matching the desired distribution of your data is to just filter what's noise in your data. So the scoring part is very important. How you're going to select what's noise and what's not is very important. So what they did is that they tested two ways of scoring the tokens. One of them is the one that I've been showing, that is using the excess loss from the reference model. And the other one does not use the reference model at all. It's just well, it uses a reference model, but it does not use the loss of the reference model. It uses the information entropy of the next token. So these are the two metrics that they consider to just rank the tokens and select top K. And okay, they just do the experiments with these two ways of scoring. And then what they found is that basically using the loss or using the information entropy yields basically the same results, so very similar. But when they try to use the intersection between these two scores, so they get the loss, they select the top K%. Then they get entropy, select top K%. So they have two sets, one selected by the loss, one selected by the entropy. Then they compute the intersection between these two sets. And they only select the tokens that are in this intersection. When they do that, when they are more rigid in the selection of the tokens, they get a little better performance with less tokens, right? Because you're just considering the intersection. So instead of using 10.5 billion, using the intersection, they get to 9 billion tokens, and they get to a little better performance. And okay, so this is also something that they explore. Let me see. Okay, here they talk about the intersection. I guess that's it about the methodology. They do some ablation studies, but I don't think they are that important. I think too much information. But anyway, I recommend reading the paper. It's a fairly easy paper to read. And in the conclusion, they say that, okay, they are proposing a selective language model that is going to be trained specifically on tokens that are more suitable for training. And they consider they have that premise that they found with that first experiment that I showed, with comparing the loss in the beginning and the training of the token level loss in the beginning and in the end of the pre-training. They found that not tokens behave equally. So that's what they consider when developing this method. And just to finish, I think this is interesting. It's in one of the appendices, but the guy of the presentation, he talked a lot about these limitations. So yeah, as you can see, they tested it on Tiny Llama 1.1 and Mistral 7B, small models, right? And what they said is that maybe these models benefit more from removing the tokens. Maybe larger models will already do that inherently. So the authors encourage people to research and try with larger models to see what's the behavior. Also, they talk about the reference model, if it is necessary or not. They say that it can replace instead of training yourself a high-quality reference model, you can also just get a model out there, like a GPT, very good model, and use it as a reference model. So they argued that that's possible. You wouldn't need to train a reference model from scratch. Another things that they considered to improve. The first thing is very basic, and it was the first thing that I thought when reading this paper. Of instead of selecting the tokens, what if we could like reweight the loss of the tokens given their proximity to the reference model? So you wouldn't necessarily remove all of them just because they're bad, but you're just gonna give different weights for different tokens. So this is something that they suggest trying that may improve robustness. Another thing that they point out is to implement reinforcement learning to do that, because you can use the reference model as a kind of a reward model, right? So integrating this reinforcement learning approach here may be beneficial. And they also argue about adopting multiple reference models, just to avoid overfitting to one reference model. You just can get like a voting system from different high quality models out there. And as I said earlier, they focused a lot about in the pre-training phase. Okay, they did that experiment fine-tuning on tool integration and everything, but the paper is really focused on the pre-training, not on downstream tasks. So what they suggest is to extend this approach of selecting the tokens in fine-tuning methods. So during fine-tuning, you also can select the tokens that are more important. So yeah, this is the overall theme of the paper. It received some critics. In the presentation, one guy I remember asked about still like the computation needed to train a reference model, to get a reference model from somewhere. This is kind of computation expensive. The author argued that you can afford that when you're doing pre-training. If taking longer to pre-train and maybe using more computation will lead to better results that may generalize better for downstream tasks, it is worth it because you will only pre-train once. So this is something that I found interesting of the guy's speech. Well, I guess that's it. If you guys have any questions or comments, go ahead.
I have a question, something that's not very clear to me. How much data in relation to the main model does the reference model should have?
They are trained on 0.5 tokens. It's fairly small, but it's fairly small, but it's curated, right? It's supposed to have only good tokens, so it does not have all the noise that a normal bigger data set would have.
But is there anything about larger models needing larger reference models, or was that not looked into?
They did not explore that. They clearly left that for future work. They point out that this method still needs to be tested for larger models. They only know how they behave in these smaller models. But yeah, possibly that will be the case, I think. Possibly if your model is larger, you're probably gonna have to have a better reference model. And for that, you're probably gonna have to train it on a larger data set, I guess.
Okay, thanks.
Someone else?
Amanda, I think I was going to ask some parts, but I think you mentioned here on the limitations of the paper that the authors already argued. But I think I would like to know about what do you think, your opinion on that, right? Because you mentioned like, oh, instead of setting to 0, you weight the tokens. But then you mentioned also the authors are concerned about if like doing this type of filtering is only worth it for small models, or if that would work for larger models. But I would like your opinion. Like, what do you think? Like, this could be something that could be added to improve LLMs, like larger LLMs that like the ones that become products, or do you think that maybe this is more like improve these smaller models that it's still very useful, because then we could improve like models that are able to run on the small devices, right? So I'd like to know your opinion.
So two things. First, one thing that they say is that they're concerned of how this will play out in larger models. And I don't think it will have the same effect that it has in the small models, because I think, and it should, it needs to be tested. I'm just saying that what my intuition is telling me, that larger models maybe already do this. They are already selective. Maybe for smaller models, yeah, completely, it's expected that it's not going to have this capability of selecting what's important and what's not. But maybe for large scale models, I think it would be already something that comes in the package, even though you're not explicitly training it to do so, I think it already selects the tokens. And about the reweighting, honestly, I think what this method is, the most interesting thing about this method is how it is effective in reducing the number of tokens needed. So as I showed, like the comparison with DeepSeek that trained on 500 billion, and then their model had 10.5 billion, I guess, and almost the same performance. If you started to just reweight, you wouldn't zero out the loss. So the loss would also be considered. So you wouldn't really reduce the number of tokens you're dealing with. And I think maybe, even though, okay, maybe it can yield a little bit better results, but then you're gonna lose this good aspect of reducing the number of tokens. So yeah, I think it should be measured, like have to find a balance between what you're increasing in terms of performance and degrading in terms of efficiency in token usage.
Yes. Just to finish here, you're talking is a completely different concept, but I was thinking about, like you mentioned, like filtering or reweighting. Kind of reminded me of regularization, which is nothing to do with the paper, right? But it reminded me, like you have like reach and lasso, right? R1 and R2, right? The lasso, it's like it's sometimes it's used for feature selection, right? Because then it's kind of heavy on the reweighting, so it kind of goes to zero the weights of the variables, right? So it's kind of like this selection of tokens. And then our reach one, it's kind of doesn't go to zero, but I don't know, it kind of reminded that it's nothing to do with the topic of the paper, but I think it's like for a very simple model, maybe it's a parallel. But Daniel?
Yeah, I noticed that they focus a lot on the efficiency of token usage, which is of course the theme of the paper. But I wonder what is the efficiency in terms of compute. Because for instance, in the beginning of the paper, they have the graph, right? And the point they say that they get a higher accuracy, and it's like 10 times faster. But also in the, can you show the plot very quick about that, please? They show like it's 10 times or stuff like that, but it's in relation to tokens used, right? But I wonder how much more compute would you need, right? Because during training, you have to also do the forward pass of the reference model. And on the other hand, maybe you can get some efficiency by zeroing the tokens if you're not using the loss of. So I'm not sure what's your opinion on that?
Yeah, I think it depends a lot. As you said, there's this overhead of needing a reference model. This for me is like the biggest overhead you can have, because you basically need to do your forward pass twice, since they're using the same base model, the same architecture, the same model size. So you're basically just doubling the time you need in the forward pass rate. Well, you could have, I don't know exactly how they implement that, if they just compute the token level losses of the reference model beforehand and just store it somewhere. Probably they do something like that, but still you need to access it. if you use what they say in the end, like you can use an API, they say about this, that you can use like call GPT API. Okay, this will be very expensive. So yeah, this is something. I'm not sure how, of course, like when you zero some tokens, you don't backpropagate the weights, the gradients in that token, right? So this is a little bit more efficient. But I don't think this matches the amount of computation power you lose needing to do the forward pass in the reference model. But yeah, they argue that is more efficient. So yeah, I'd have to test, really test by myself to see that. But yeah, it seems that it's faster anyway.
Yeah, because in AI, there is like this really frustrating recurring theme that simpler ideas just scaled up often perform better than. We like to make these sophisticated ideas and we understand how inefficient things are. But then it's very frustrating that when you try to apply it, it doesn't scale so well, and often the scale outperforms, right? It's very frustrating about it.
Yeah, I think it would be very interesting to apply the same method to a larger scale model. I'd be curious to know what happens if the results still hold for a larger model in larger data sets also, because they're fairly small data sets, right? Less than 10 billion tokens.